Okay, well, thanks everyone for dialing in. Happy 2022. This is our first Friends of Lunar Volatiles meeting of 2022, and it's going to be a very good one because we have with us today Dr. Emily Costello. I'll introduce Emily briefly, but I'll let her introduce herself in more detail as well. But Emily is at the University of Hawaii, and she's an expert on all things impact gardening. And she's going to be talking to us today about some of that work, including a recent paper which looked at the effects of impact gardening on ices in permanently shadowed regions. So I will hand it over to Emily. Just a couple of the usual reminders. If you're not speaking, please go ahead and put yourself on mute. Videos, cameras can be on or off, totally up to you. Feel free to drop any questions and such in the chat. And Emily, would you prefer if we held questions until the end, or is it better for you if we interrupt with questions? We can do either.
I think it's going to be a pretty short talk, so we'll have plenty of time for discussion. So maybe let's do questions after.
Sounds good. All right, so we'll hold questions until the end. And if there's anything in chat, we won't look at it until after the presentation. So with that, I will go ahead and put myself on mute and hand it over to Emily. And Emily, thanks for joining us today.
Yeah, thank you, Pavati. All right, hello everybody. I'm Emily Costello. I'm going to quickly turn off my video here to save on bandwidth when I start sharing my screen, but hello. Sometimes it's nice to see somebody's face before they start talking at you. So here we go. So can I get some confirmation that we can see the slides now?
Yep, looks great.
Okay.
On screen. All
Thank
good.
you so much. Okay, so thank you for inviting me. Thanks for letting me come speak with you guys today. I'm Emily Costello. I'm a postdoc and affiliate graduate faculty at University of Hawaii. And today I'm going to be stepping up on this digital soapbox to enthuse and emphasize about the importance of impact gardening for lunar exploration in general, and specifically for the Friends of Lunar Volatiles. Impact gardening is an important process which is shaping the surface of the moon and has been shaping the surface of the moon. So when we're thinking about where the volatiles on the moon are, how they've evolved, how they got there, and where they are now, impact gardening is an important piece of this puzzle. So I'll be sharing the results of a recent publication with all of you. This was a publication in JGR, and I saw that Pravati put the link to this publication in the email. So that's great. Thanks for doing that. Just as an introduction, impact gardening is the process by which repeated impacts mix and churn the near surface of bodies across the solar system, including the moon. I've got a little schematic here which shows an impact excavating a crater, ejecta burying material which was on the surface. Now, gardening is this mixture of excavation and burial. Over time, repeated impacts will mix surface material down to greater depths and excavate buried material up and bring it towards the surface. And over time, the surface regolith is changed physically, chemically, and thermally. So impact gardening is churning material up to the surface, churning material down to depths. Now, in this recent publication, I built on an existing model of the rate with which impacts excavate. But I built on it by modeling the rate with which impacts bury under ejecta. Then I assessed the implications of both excavation and burial impact gardening for ice on the lunar poles. So gardening has been proposed as a mechanism by which polar volatiles can be sequestered from the relatively hazardous surface environment on the moon, where temperatures are usually relatively high and volatiles are exposed to the flux of micrometeorites, possibly photodissociation. So the surface is not the best place for volatiles to exist, and impact gardening would shield volatiles by burying underneath ejecta, and possibly transporting volatiles to greater depths. The basic idea for this idea of sequester by impact gardening comes from the fact that ejecta covers a larger surface area than the area that's excavated by any given crater. I've got a little figure here which represents this big blue circle. This is the ejecta coverage circle. And this little white circle is an excavation circle. You can think just from this little picture, we can see that burial is covering a greater surface area than excavation by a crater. But if we keep drawing circles on this slide, we can imagine it would fill up with the blue of covered by ejecta faster than it would fill up with the white of excavated by a crater. So thinking of the problem this way, it seems reasonable that burial would outpace excavation, and volatiles on the surface would be buried underneath ejecta at a quicker rate and to greater depths than they're excavated by craters, just from the surface perspective. The gardening model that exists predicts overturn, and this was published in 2018 and expanded on again in 2020. This model describes the frequency with which a point at depth is excavated by impacts. It's just these little white excavation dots. And it describes the frequency that a point at depth is excavated as a function of time, the impact flux, and the parabolic geometry of transient crater bowls. One of the main updates for this model was including the flux of secondary impacts, which especially at the meter or so scale, where gardening is dominantly occurring, secondary impacts are a really strong contributor to this. To model burial under ejecta blankets, we took the same statistical underpinnings of the model of overturn and of excavation gardening, but we updated the geometry. So the geometry was updated to represent annuli of continuous ejecta, these little donuts. We used the geometry of ejecta thickness from McGetchen et al. And approximated ejecta thicknesses for 4 different annuli, which I've represented here. The figure on the screen shows a visualization of the continuous ejecta approximation and how we broke it up into pieces in this paper. So like I said before, we used the same statistics underpinning to describe the frequency with which a point at depth is buried underneath ejecta by a continuous flux of impacts. We then solve for the depth of any given point is buried under ejecta as a function of time. Now here's a plot of the results. On the horizontal axis, this is time progressing to greater lengths of time as we go towards the right. And the vertical axis is the depth of impact gardening. It's labeled excavation type impact gardening in red and burial type impact gardening in blue. Now this plot is impact excavation and burial as a function of time for a case where regolith is being mixed. So mass is always conserved between the excavation of material and the emplacement of the ejecta blanket, but volume isn't necessarily always conserved. We can imagine that when an impact strikes rocks, it would have a higher density or a smaller volume excavation and then fluffier ejecta. But in this case, we're imagining that ejecta volume is equal to excavated volume, where regolith is just being mixed. We also plot here the apparent gardening from the Apollo cores. These are those black boxes, data points. Now these Apollo cores represent the validation data set, which we endeavor to reproduce with all of our impact gardening models. Now the red line, which I've labeled excavation, is the result from our previously published gardening model. And note that even without burial under ejecta, we had a pretty good fit to those Apollo core data, but we were maybe a little bit over predicting the extent of gardening. The blue line here is the burial underneath ejecta. And the top right of the figure, the colored dotted lines, these are model predictions for the burial rate under ejecta annuli, as they're described as A, B, C, D. And then the sum of all of those burial under annuli is shown in blue, and that's that burial sum line there. Now the average of excavation and burial gardening is shown as a black line and fits the gardening implied by the Apollo cores really well. This is a great result, but there's another implication here. At all time scales, excavation is deeper than burial. This conflicts with our previous notion when we were looking at just the two-dimensional surface of annuli of burial ejecta annuli accumulating on that surface being larger in surface area than the surface area that's excavated. But when we bring in the third dimension, we found that excavation is faster, it's deeper than burial is. Now this means that impacts are excavating material below ejecta faster than ejecta is accumulating. And the net effect of impact gardening in regolith is a cycling towards the surface, not a sequester of surface material towards depth. So if we think of just space weathering, where we're accumulating the physical and chemical changes of space weathering at the surface, we would see fresh material brought upwards to the surface and at a rate faster than the space weathered material is brought down into the core. And we also modeled a case which was more favorable for faster burial. That is when rock is being turned into regolith. In this case, while mass is conserved, the more dense excavated volume is smaller than the fluffy ejecta volume, which is regolith. So although burial and excavation are closer in this scheme, they're closer together, excavation is still deeper at all time scales than burial. So impacts are excavating below ejecta blankets faster than the ejecta blankets themselves are accumulating. And this makes some sense because if you think about not just that flat surface area argument, but a third dimension, the ejecta volume is going to be deeper penetrating than the thin volume, which has been spread out over a larger surface area for an ejecta blanket. Now, what does this mean for polar volatiles? We're the friends of polar volatiles here. This is what we really want to know. So volatiles at the surface are relatively unstable compared to volatiles which are at depth. If the net effect of impact gardening is to cycle buried material upwards, then gardening will have an important implication for destabilizing volatiles within at least a meter deep column of the regolith. Now, gardening is not necessarily, like us, a friend of lunar volatiles. The more intense gardening will mean more time spent at the uppermost surface, while less intense gardening will mean physical disruption of perhaps previously coherent, pure mercury-like ice deposits. So you can quantify the intensity of impact gardening by, and we do so by labeling these gardening zones, where intense impact gardening is within the in situ reworking zone. We borrowed terminology from Morris 1978 for the definition of this intense gardening in the in situ reworking zone. Now this intense gardening fits with the gardening apparent in the Apollo cores. Again, they're plotted here as these black dots or black squares. We also introduced the degradation zone. Inside the degradation zone, gardening is less intense, but it has occurred to some extent. And the depth of the modeled degradation zone is in agreement with the timescale over which density anomalous cold spots and crater rays fade into background regoliths. So I've plotted those here. All of the material within the in situ reworking zone has been intensely mixed. Material within the degradation zone has been somewhat mixed. Ice inside of the reworking zone has likely been physically and thermally destabilized by at least one impact and spent a significant amount of time at the relatively unstable uppermost surface. Ice inside of the degradation zone has likely been pulverized by impacts, but possibly is likely less physically and thermally destabilized than material which was in the in situ reworking zone. So we're unlikely to find coherent pure ice deposits anywhere between the surface and the bottom of the degradation zone. It's still possible that we would find horizons of pulverized ice within the degradation zone. Now, this plot can also be interpreted to understand the fate of ice which has been delivered. So for example, I've got a blue line here, which assumed that maybe the Tycho impactor deposited ice on the moon. So this ice, deposited about 100 million years ago, would have been broken up and distributed within the top 2 meters and depleted within the top 20 centimeters. We also extended our impact gardening calculations back in time by scaling the impact flux with the Neuken et al. 2001 crater production function, which described how the impact rate was higher in early lunar history. And I've got a plot here, which is expanding that time scale back towards past 3 billion years ago. Now, ancient ice will have been pulverized as deeply as 10 meters by impact gardening in the degradation zone, and depleted as deeply as 1 meter by impact gardening in the in situ reworking zone. Now, I've discussed how this model can be used to predict the distribution and nature of ice at depth, but it's also important for us to interpret the results for future lunar exploration, particularly future cores. So knowledge of the gardening which has shaped a core will be critically important for interpreting implications of any discoveries of the source, age, and spatial distribution of ice across the lunar polar regions, because impact gardening will have been shaping those cores. Another important thing I think we need to think about in the context of impact gardening and volatiles is that it's a continuous process. So ice, which is apparent in a pixel of spectra, for example, doesn't necessarily imply that there is ice directly below that pixel, because impact gardening has been rearranging the distribution of ice over the last amount of time since that ice was delivered. So again, my name is Emily Costello. I'm from the University of Hawaii, and I'm really looking forward to your questions and discussion on impact gardening.
All right, thanks, Emily. That was a really good refresher of the paper, which I also put the link to in the chat, and you can see the little Zoom applauses from everybody. So we have plenty of time for questions. So folks, if you have questions, you can either raise a hand or put the questions in Zoom, and we can ask Emily questions. All right, so I see Tim Leidengood has his hand up. Tim.
There we go. Emily, I'm afraid I wasn't paying as close attention as I should have been on your very last slide. Could you repeat what you were saying about detecting the spectrum of ice within a pixel?
Yeah, so especially for Trailblazer, right? We want to know if we see ice in a pixel, it doesn't necessarily mean that there is ice below that pixel. So at the uppermost surface, you might see some surface frost, but seeing surface frost does not necessarily mean that if you were to dig a hole right under that pixel, you would find more ice, because impact gardening will have been rearranging both in depth and horizontally the distribution of the ice.
Okay, thank you.
And I see Michael Poston asks in the chat about implications for Mercury, and he clarifies the planet, not the element.
Yeah, so we had a publication in 2020 where we explored the implications of impact gardening for polar ice on Mercury. In that we found that impact gardening is relatively shallow on Mercury, and we were able to expand to look at there on Mercury some thermal lag deposits, which are at lower latitudes and are not associated with radar signatures for ice underneath, which could be interpreted as locations where ice used to be, which has since sublimated. And by assessing the thickness of those deposits, we were able to calculate that gardening would have destroyed them completely, would have blasted them to bits and mixed them with underlying regolith over about 200 million years. So since they're still visible on Mercury, we were able to say that gardening supports the hypothesis that Mercury's most recent large-scale ice deposition occurred no more than about 200 million years ago. So we do have a paper about Mercury where we give it its due diligence.
Awesome. And I see we have a couple of hands up, so we'll go to Carly and then Liam.
Oh boy, okay. This is great fun, Emily. I sort of following up on some of the questions that Tim raised. I'm thinking about, okay, you've got a concept of what happens stratigraphically at the poles. And you point out that, well, it's not going to be the same thing all the way down. Well, as you know, assuming Artemis goes and the astronauts are able to go and get samples, some of the samples they're very interested in is a core. Okay, so what are your recommendations of how they should be approaching preserving the stratigraphy that might be there?
So all of my modeling is an effort to reproduce the gardening which is apparent in the Apollo cores. So the Apollo cores did well. We were able to see the apparent gardening, and although the Apollo cores are can't be necessarily connected even between spaces, their stratigraphy, there is a signature of impact gardening where the intense mixing zone correlates with the age of the cores, or the exposure age of the cores. So I don't know much about collecting cores. But since it's been done before well, I can imagine that any further cores would be fabulously interesting to look at.
Well, for example, during Apollo, they had the little narrow cores that went deep, and then they had the wider cores that were a little bit shallower, but they had spatial width to them. If you had your preferences, would you prefer one over the other, or?
Deeper. I'd prefer deeper rather than wider.
Okay, that's a good data point.
Yeah.
Thanks.
Yeah, thank you.
Yeah, interesting. All right, so let's do Liam, Tim, and then I will, or actually let's do Liam, then I will read Brad's question in the chat, and then we'll go to Tim. Liam.
Okay, great. Yeah, Emily, thank you for the talk. I'm going to switch up the kind of topic a little bit. I'm curious about the crystallinity of the surface. And there's assumptions a lot of the time that the surface is amorphous because it's been weathered. But then I'm curious whether impact gardening, or I guess these kinds of impacts, are possible to kind of get rid of the amorphous material and potentially expose the surface to crystalline, and whether, or if the impact gardening itself is so intense that the newly exposed stuff will have so much damage that it kind of maintains an amorphous rim. Like basically we hear of this concept of an amorphous rim, but I'm curious if it's constantly maintained or if it's only the weathering after the impact gardening has exposed it. So yeah, just curious on your thoughts about that.
Yeah, we might be thinking about a little bit different scales for,
okay, interesting. Yeah.
For this. So gardening is mostly driven by secondary impacts. These are relatively low energy. And the scale of gardening that you look at is generally from centimeters to meters.
Sure.
It's not necessarily at the grain scale. But there are ways that we can think about the rotating of grains in impact gardening, and there are publications which have looked at this.
Yeah.
So how grains are rotated and how they're exposed to space weathering at the surface,
I
and
guess
then transported to greater depths. Or sorry.
Yeah, so I guess, I mean, another way to think about it is if the amorphous rim is shallow and much smaller than the scale that you're talking about, and if you're going to impact garden and re-expose things that were at depth, then would you think that that whatever's been re-exposed would be crystalline to begin with? I guess that's my question.
If you break off the rim?
Yeah, sure. But the rim's not there if it's been gardened at a certain depth, right? Because the rim is just on the surface.
Right.
So if you expose something at depth, then is it that I think about it from the concept of kind of like the volatiles, the way that they're bonded to the surface is very dependent on whether it's a crystalline surface or an amorphous surface. And there's been this theory that impact gardening may be exposing kind of crystalline material because it comes from a depth. And if you're talking about centimeters, then you're talking about beyond an amorphous rim. So it seems like that would be the case.
Yeah. Sorry, I think I was just thinking in a different scale. Yes, absolutely. Gardening is bringing up crystalline materials to the surface.
Okay, that is exactly what I was asking. I simulate on the scale of atoms, so we're definitely two different scales, but very interesting to kind of think a little bit more macro. So thank you. Yeah.
Yeah.
Great. Nice variety of questions. Thanks, everyone. This is interesting. All right, so I will read the question that Brad Blair asked in the chat. So Brad asks, Emily, have you thought about how to measure and or calibrate your model? Specifically, could you use a combination of polar wander and your model to explain the Clementine LR radar measurements?
Ooh,
Hmm.
that's really cool. I haven't thought of that before. So up until now, we've been using the Apollo cores as our main validation data set. So there are these publications which show the depth of the in situ reworking zone, and that is what we've been trying to reproduce. We also compared to the erasure of surface features, so the erasure of diviner cold spot thermal anomalies and the disappearance of lunar rays. And our models generally agree with the disappearance of those. But moving forward, I can imagine there's plenty of really interesting questions and ways that we could explore this. I've never thought about lunar polar wander and trying to match those observations. So cool.
Cool. All right, so I see Liam and Tim both have their hands up. I think Tim's is a new hand. Liam, was yours just the hand
Mine's
from
just
before?
the residual hand. I'll take it down.
Residual
Make it-
hand. All
Yeah,
right.
that's a new
Tim's-
hand. I
Tim's
put it
is a
up
new
again. Well, partly inspired by Liam's question, if I may, I'd like to take advantage of the presence of our audience and the experts in it. But when we're talking about these length scales of different things, of course, Emily's talking about things that are at least centimeters and bigger. But perhaps Carly could enlighten me. How thick does a layer of frost need to be detectable as a frost spectroscopically in the reflected light off of these little grains? And then how thick does a layer of hydrated material need to be for us to perceive it in its spectra?
It depends on the other dimensions, because you've really got 3 dimensions you're talking about.
Well,
And
let's assume it's horizontally uniform.
okay, well then, yeah, just I'm pulling a number out of the hat here, so to speak. It can be just a frost, a very thin layer of frost. I mean, you can see that with your eye. If you go out, in the morning and there's been a frost, you can see the frost. Well, spectrometers are going to see it even more prominently. So it doesn't have to be a lot. But getting at your general question, which is, okay, well, what is the detectability level? And then we have to think about, well, okay, let's step back a little bit. If we take a regolith, like what Emily's working with, which is a lot of particles, typically a photon coming in will interact with several before it's reflected back out. But it won't go deep, it'll only go, 10, 20 particles away before it's scattered back out. So it's still surface, but it does depend on the particles and how transparent they are, et cetera. So then we translate your uniform thickness to, okay, well, how spotty can it be before you can't see it anymore? And I can't do that off the top of my head.
I guess I'm still wondering, is the relevant unit here, is it tens, hundreds of microns, smaller or bigger?
You mean in terms of the depth that it'll penetrate?
Yeah, I mean, so we have to have a coating of individual particles. So even though there's a lot of particles and it can penetrate through the pore spaces, an individual particle would be coated to some extent. And it's never been clear to me how thick that coating on particles would be in order for this to become a detectable phenomenon. Is that, you mentioned frosts that I can see. Well, I can see that they have thickness too. So there we're talking about something that's, minimum around 100 microns.
Yeah, I don't want to answer that without data.
I thought you had 30 years of data in your head.
Spoken like a true spectroscopist.
Okay.
All right, and Norbert has his hand up.
Oh, hello, yes. So for these, one important number for this impact simulation is how much of the ice is really lost during impact. So on Ceres, for example, we see that the fresh ejecta have more ice than the older surface, right? So that's one reason of many to think that the impact itself devolatilizes very little of the ice. So it makes sense. It might make sense to run with simulations assuming, only 5% or so of the ice got lost rather than. So are you assuming 100% of the ice get lost now, or from impact immediately?
We don't necessarily assume any ice is lost. We just say impact gardening is intense in this zone, and therefore it's more likely that ice has been devolatilized from this place or these depths.
So if you impact ice, you lose 0% of that?
We haven't put any numbers on the exact amount of or volume of ice which is removed for these simulations. So we can think more generally that because it's not well known, we did in this paper show that even a secondary impact could vaporize ice that it's struck by. But we didn't make any claims about whether or not there's a volume of ice in these zones or not. Just that if it's intensely gardened, it's less likely to have significant amounts of ice. If it's somewhat gardened, it's unlikely that we'll see coherent deposits which haven't been broken up mechanically.
So Emily, if is the right way to think about that then that when you're considering the excavated volumes, you're kind of agnostic to what the volume is composed of? It's just
yes.
So you're just looking at is the volume affected or not?
Right.
Is that right? Okay.
Yeah.
Michael has his hand up. Michael Poston. So Michael, I see you unmuted, but we don't hear you. Oh, mic issues.
Well, I can follow up a little on what Norbert was saying too. Moving forward, what we want to do is put numbers on these and understand better what an impact implies for the actual mass or volume of ice which is in these zones. So that's ongoing work.
And Mike Barker has a hand up.
Hey there, can you hear me?
Yep.
Yeah, Emily, nice talk. So maybe this is kind of related to what you were just saying, but is it possible to link like an observed sort of abundance in terms of area on the surface to the age of the deposit or the age of the ice using your model?
Abundance on the surface. It would be, I think, more direct to look at cores and be able to compare. So the location and diffusion of ice within a core would be easier to backtrack to the model's description because the surface is so changed and so stochastically changed. I think the surface would be a really difficult place to be able to back out from. But if we had that third dimension, we had the depth dimension, it would be relatively simple to compare to the gardening predictions and speak to the timing of the delivery event.
Okay, thanks.
So I guess just by looking at, like, I wonder if, so I guess what you're saying, Emily, is that you can't really use the lateral heterogeneity as a proxy for having a core. So you can't sort of look at how patchy the ice is and get an age from that, or that's tricky to do.
I'd have to think about that, but I think that it's a more simple and direct comparison to our model results for a core. And we haven't necessarily thought about or looked at comparing to the surface patchiness. Doesn't mean it can't be done, but
Awesome.
Yeah, it might be interesting to know more about that, because that's
Yeah.
sort of more observable from a remote
Yeah.
sensing perspective.
Yeah. And Rosemary. All right, everyone has to ask a question now because
Yeah, I want to go back to something you said, that Mercury's surface should be gardened to shallower depths than the moon. Is that what you said? And why?
right. So at the scale of gardening is based on the scale of the impactors which are striking. So micrometeorite flux on Mercury is much higher than on the moon, but a publication which we used was Marchi 2005, which describes that between sizes of 1 centimeter and I think it was 1 kilometer, there is a dip in the impactor population, which would shift it so that Mercury at the scales of gardening from the centimeter to meter scale, which is what we were looking at, would be slower on Mercury than on the moon. So it's a function of the flux. And although there are details with the size ranges, which Mercury does have a higher flux, at this scale that we were looking at, it's not as high, but it's definitely worth looking again at Mercury, especially in light of the way that secondaries behave differently on Mercury. So secondaries are the dominant drivers of impact gardening at these scales that we're interested in, centimeters to meters. And they don't behave the same way on the moon because Mercury has higher gravity. So they are not dispersed as evenly. There might be more intense gardening near craters. These are things which we haven't necessarily been able to include in our models yet, but are something that we really do need to look at.
Okay, thank you.
cool. So I have a question. So mine's kind of a basic question, and I feel like I've asked you this a few times before. But so could you go back to the slide that you had with the dotted lines and the different colored lines? It was like
This one?
yeah, no, yeah. This one's good, right? I think you had one earlier, which was just the one on the left, but either of those is fine. So I sort of have to orient myself to this every time I'm thinking about gardening. So I figured I'd ask the question in case anyone else is wondering the same thing. But could you remind us of the right way to read one of the charts like this? So for instance, so if I'm looking at the red line, I can see that a time of 10 million years corresponds to like a depth of 10 centimeters. But how do I express that in words? So is that saying that a patch of the surface that is 10 million years old is almost certain to have been gardened to a depth of 10 centimeters? Is that the right
patch
way?
of surface which has been exposed to the impact flux for 10 million years will have been gardened intensely down to 10 centimeters. Another way you can think of it is everything along this line, this depth and deeper, and shallower, sorry, this depth and shallower has been intensely gardened over this time scale. Mm-hmm. And we tried to make that a little easier to think about by defining these zones, right? Like it's harder to think about just the contour. Mm-hmm. But by defining the zones, it's everything that's within this zone and shallower has been inside of this intenser working over this time scale.
Yeah, I always think you do a great job of reminding it, and every time you say it, it makes sense. But then when I don't have Emily's voice in my ear explaining it, I always forget. So I keep trying to make sure I get it right. So another question, and this might be because I'm not thinking about it hard enough, but so you have this relatively shallow in situ reworking zone, and then below that you have this degradation zone. And I think I'm thinking about this conceptually the wrong way somehow, but basically what I'm thinking is, well, if everything near the surface is reworked so intensely, then why is it that the stuff even deeper down is just degraded and not, because it's at some point the stuff in the reworking zone depth gets down to the degradation zone depth, but it's not like the ice comes back. So I guess, I'm just like having trouble putting that into words in my head.
Yeah. Okay, so maybe it's helpful to think about the Apollo cores. The Apollo cores and what these data points represent. I wish I had a picture, sorry, there's this beautiful Apollo 16 core, which just shows this perfect gradient of dark, reddish, space weathered material, and then whiter, unweathered regolith below. And that's where these data points are coming from, is the mixing of these materials. The zones and the horizons of in situ reworking are also informed by cosmogenic radionuclides, and we know that they're homogeneously distributed within the in situ reworking zone. That means that some process has been mixing them to greater depths than cosmic rays could be making them. And in the degradation zone, we see horizons of relatively unweathered material with horizons of weathered material. But it's patchy and there are heterogeneous horizons. But within that in situ reworking zone, it's homogeneous. It's been intensely mixed. So for me, I always have to refer back to the Apollo cores and what they're telling us to interpret what's going on here. And in my brain, when I look at this, I imagine, okay, I've collected a core that is a surface which is 100 million years old. I will see cosmogenic radionuclides reworked homogeneously down to 20 centimeter depths. I'll see horizons of patchy material to about 2 meters. And then below that, we'll see pretty fresh material, which may have just been completely crunched up by the ancient impact flux, but hasn't been cycled up to the surface in the same ways that these upper sections have. So I always try to imagine a core which has been taken when I'm looking at these, and that helps me a little.
That's super helpful. Yeah, I guess one more question is, can you say anything from your work about the rate of volatile deposition required to preserve, a coherent stratigraphic layer? Or, because you can say something about the age, but does your work say anything about the rate at which volatiles might have had to be delivered?
It can, but maybe not directly. So without having something like Norbert was hoping for, where we say exactly how much mass is removed or transported and moved around, we can't really say how much mass needs to balance to match an observation. Say we see this much ice, then gardening says that this much should have been removed. Models of delivery say this much should be delivered, therefore there had to be this much to match what we see. We don't have the handle on how much is removed by gardening to be able to say that, but what we can say is that impact gardening mixes quickly and is continuous, and because the gardening is driven by a exponentially shaped impactor population, little impacts are much more frequent than large impacts. And in that Mercury publication, the Mercury Moon publication in 2020, we explored this a little more, where we compared the rate of continuously delivered ice and how thick a continuously delivered ice deposit would grow over 1 million years or so, 10 million years. We compared it to impact gardening over that same 10 million years or so. And a continuously delivered source, although if you're given 1 billion years, you could you could accumulate a meters thick ice deposit. Impact gardening, because it's affecting those small scales faster than it's affecting large scales, is mixing those small, continuously built up layers into underlying regolith faster than those continuous sources can deliver them. So over 10 million years, say, we've got a 5 centimeter thick ice deposit. Well, impact gardening will have gardened the top 20 centimeters, mixing underlying regolith in that ice together. So if we're looking for pure coherent ice deposits, continuous sources couldn't do it compared to gardening. But an episodic source, which delivers a huge volume of ice in a geologic instant, like a comet impact, which would deliver, let's say, a meter thick block of ice into a polar, permanently shadowed region. That meter thick block is exponentially more durable against impact gardening by those tiny little impacts than a tiny thin layer, which is built up over time. I think I remember from those calculations that that meter thick a block wouldn't be destroyed over 1 billion years, while a meter thick block would never accumulate by continuous sources because those small little layers would be mixed with underlying regolith faster than they could build up.
Cool. And I see Julie Mitchell has a question in the chat. So Julie asks, do you think different volatile compounds would be vaporized and redeposited at different rates and distributions? Could there be some selecting of certain persistent stable species, for example, water, versus others that are much more volatile?
Yeah, that's an absolutely interesting thing to think about. And I think that is the next step. Like Norbert was saying, we need to think more about where the ice is actually going, what the impacts are actually doing to the volatiles. And this detail of the different species and how they would be interacted with differently would be really fascinating.
Yeah. I agree that would be super interesting. But, I also think one of the neat things about your work is that I don't think I fully appreciated until Norbert asked his question and you answered that it is material agnostic. And so what in situ reworking means for water ice versus something else could be different. And so yeah, and that's very cool. Right, we have time for a couple more questions if folks have even more questions. But thanks, Emily. This was a really good presentation and a really good discussion. And
great discussion. Thanks, everybody.
Yeah, and the link that I put in the chat earlier is the same as in the email. So that's Emily's most recent paper, but she has several other papers explaining the model, its applications to the lunar surface in general, and also to the surface of Europa, is if I remember right.
Yep, that's right.
Awesome. All right, so we have around 10 minutes left. So if anyone has any other news or anything else they want to share, we have some time for other items. And while folks are thinking of things, I will just mention, especially since we have our friends from Hawaii on the line today. So the next month's Friends of Lunar Volatiles call it's going to be the Monday after LPSC. It's going to be quite late in the evening for East Coast folks. I'll send out the time later, but it'll be perfect for folks in Hawaii. But the reason it's so late is because our presenter in March will be someone from the Chang'e 5 team, and so they'll be talking about the recent observations by some of the spectroscopic instruments on Chang'e 5. So Chang'e 5 was a sample return mission, but there was a recent paper that sort of looked at some in situ data that was collected during the mission. So they basically looked around the surface and saw a hydration signature around the location where the sample was returned from. So we'll hear more about that in March. But yes, any other news or anything else fun or volatiles related to share?
Parv, this is Brad. I guess I would think that given a Viper mission in a drill, that Emily's paper addresses issues that are at the scale that Viper could sense, and coming up with some type of a way to publish, either a predictive model or a way to sort of guide the Viper team. Let's say you find a recent crater that has done impact gardening, if there's a way to maybe think about how to use that mission to gather data to validate the model, now is a good time to publish that before it lands. And then this issue of other volatiles is very near and dear to my heart. And Parv, I would encourage you to maybe find someone in the community that can present on one of the upcoming Friends of Lunar Volatiles, maybe some maybe preliminary research that deals with this issue of, you know, what gets volatilized under what conditions. And I think that's a core issue for the ISRU community is going to have to deal with that, whether they want to or not.
Yeah, and I know this is something Julie has done a lot of work on when she and her team are thinking about curating the Artemis Isis. Like, Julie, I know I've seen you present a couple of times about just, you know, the range of different volatile species and you know, their volatilities. Do you have a recent paper on that, or, you know, is there something we should look up or look forward to in terms of presentations or papers? I didn't mean to put Julie on this, but actually, I think Julie had to drop off. So, but yeah, but good point, Brad. And I think I've heard Julie Mitchell present on. I know it's something that she and her team are thinking about when they're planning for curating return samples. So, so if you see Julie Mitchell presenting on an agenda sometime, check and see what she's talking about, because it might be related to different volatile species. But yeah, what else? I guess the other tangentially volatile related thing to watch out for might be, I've been trying to figure out if LRO LAMP might be able to see any volatiles released by thermal heating due to the rocket booster impact that's coming up on March 4th. So I'm not, so jury's still kind of out on that, but it's just something I've been thinking about, and interesting problem to think about.
Are you thinking about chemistry involved there, like Gladstone did with L-Cross? Or are you just thinking about if the molecules are there and are released thermally?
Yeah, that's good question, Michael. So I think mostly what volatiles might be released thermally, because, you know, it's sort of it's a near equatorial impact. And my understanding, based on reading some of the L-Cross papers, is that at the relatively low impact velocity that this booster is coming in at, you know, it's my feeling is it's not high enough to really drive chemistry, but it could sort of, you know, that you'll have a thermal wave that'll desorb stuff, drive it off.
Yeah, so the Gladstone paper from Melcross had a temperature for the chemistry that they think they saw with there. I don't want to say the wrong number on the spot though.
Cool. Yeah.
Parvar, let me put a little plug in here too. So it's related in that we know what LRO has been able to do for lunar volatiles, and it's been wonderful, but it's not going to last forever. And we have a workshop coming up, beginning, the league is starting an activity asking, okay, what sensors would we like in the next decade to look at the moon? So people who are thinking about volatile sniffing, please be thinking about submitting a white paper discussing things that should be considered, because this is the opportunity to do it.
Yeah, thanks, Carly. I'd forgotten about that, but yeah, but that's definitely something that's relevant to this community. And I just looked at the registration link for the kickoff meeting next week for that special action team that Carly mentioned. And so that link is in the chat. And yeah,
Okay.
I'm hoping to attend, and definitely encourage everyone else to do so. And if you can't attend, submit a white paper and
Yes, thank you.
participate in other ways. Yeah, thanks, Carly. And what else? Are folks going to LPSC in person?
What's the deadline for deciding?
Depends how close you are to Texas. I guess you could just drive down, Michael. But yeah, but I see Ali gave a thumbs up, so I think that's a yes. I'm thinking of going in person. We could catch up over Volatiles sometime, whichever of us are going. But yeah, all right. So we are coming up on the hour, so I won't keep everyone too long. But thanks again, Emily, for a great presentation. You have lots of appreciation in the chat from everyone. And so take care, everyone, and we will see each other again in March. And maybe some of us will even see each other in person or even virtually at LPSC. All right, let me stop the recording.
Thank you, Barbara.
Thanks, Rosemary. Thanks, everyone. Take care. Bye-bye.